Welcome everyone to DIGA694 Capstone Research Presentations. Throughout the period tonight, we'll feature several graduate candidates as they present and defend some of their preliminary work with their capstone projects and results. So with that, we'll go ahead and jump right on in here to our first presenter. And I did want to share my screen here briefly to give everyone an idea of the schedule of the evening. First off, we'll have Sarah Waterman presenting her work on performance of the, I'll just say the ARIMA, Sarah for the acronym, the ARIMA, and convolutional neural network models for sales forecasting. So mouthful certainly there, but nevertheless, some really interesting statistical and applied analytics to this topic, followed up by Per Lundmark with some remote sensing of forest carbon. And then we'll take a short break, followed up lastly with Annika with some COVID vaccination site analysis. And then lastly, Ian Robertson with supervised image classification. So with that, Sarah, I would like to turn it over to you to discuss some of your findings on the ARIMA convolutional neural network. So a really cool topic. So Sarah, I'll turn it over to you.
Thanks, John. Get my screen shared here. All right. Can everyone see?
Yep, we're all good to go there, Sarah. Yep.
All right. So as John mentioned, I'll be talking about the performance of ARIMA and convolutional neural network models for sales forecasting. So we'll first go through the introduction, then the methods, results, and then we'll talk about some conclusions and discussion surrounding the topic. To the introduction. So what is sales forecasting exactly? Essentially, it's making an informed and methodical prediction of what future sales could be. And it's the base of any business plan because it allows companies to prepare to have the right amount of labor, secure supply chains, and things like that. So some factors that impact forecasts are the behaviors of competing businesses, the cost of inputs, inflation, seasonal variations and trend, pandemics as we've seen in the last few years now, and the time period that you're forecasting for. There are typically two ways to forecast sales or forecast anything really. The first way is statistically, and this is usually done for linear data, but you can also use machine learning, which can be done for linear or nonlinear data. So out of all of the model options, and there are quite a few of them, ARIMA and CNN were chosen for this project. ARIMA is Auto-Regressive Integrated Moving Average. It was created by Box and Jenkins in 1976, and it's generally the most effective statistical forecasting method. It generally outperforms all other statistical methods when compared with them. It's kind of a hybrid method because it combines auto-regressive and moving average methods, which are individual methods, and it expresses future sales as a linear combination of past seasonal and non-seasonal observations of a time series. And then convolutional neural network was also chosen for this project. There are a ton of different neural network models. They are all based on the way the human brain processes information. So input variables are designated as neurons, and the model derives patterns and trends to make a prediction. CNN specifically has stronger usability than other neural network methods, and it also does not require extensive knowledge of the input data. So that's why it was chosen for this application. So the project intent was to explore ARIMA and CNN forecasting models using data from an anonymous company, which I'll just call Company A. One of the goals was to determine which model performs the best based on RMSE, MAE, and MAPE performance scores. Best here is defined as which model has the least amount of error, so the least distance between the observed values and the predicted values, and that is measured based on those three scores there. Another goal was to determine which model is the best for use for company A, considering data compatibility, usability, and also performance. Onto the methods. So all of the data that was used was pulled from the company A database, and it was masked prior to use. They provided 100 each of customers and SKUs, and those were chosen using simple randomization. For customers, the variables that were pulled were customer ID, invoice month, extended sales dollars, average sale price per item, freight dollars, business days, and the number of invoices. Those were essentially just the variables that were available. For SKUs, it was the same thing with an additional 2 variables, which were the number of customers and the number of branches. And then 5 years of data were supplied for all of those customer SKUs and all their variables. It ended up being between the 1st of 2017 and April 30th, 2022, which is a total of 64 months, just over 5 years. Because some of the randomly selected customers and SKUs were missing several months of sales, or they were missing certain variables, there ended up only being 95 customers and 93 SKUs as opposed to the original 100 that were requested. So to prepare the data, several steps were taken. The first step was to decrease the time frame to 60 months to allow for the conversion of data to 3D for CNN models. CNN models must, or they require 3D data rather than the 2D that the data was originally structured as. So it had to be decreased to 60 to allow the data to be broken into 12-month chunks. So that was done for CNN, but it wasn't necessary for ARIMA because ARIMA can take 2D data. After that, some values from 2020 were replaced with values from 2019 of the same month, where COVID effects were significant enough to skew predictions. So the goal here was to minimize the effect of COVID without losing any data. Some other studies had completely just cut out the year 2020, but since there's only 5 years of data here, the values were replaced with previous values instead. And then the data set was split into train and test data sets. The train data set is what trains the model, and then the test data set is what you can compare the predictions to assess the efficacy of the model. 80% of the data was designated as train data, and then 20% was designated as test. The next step was to remove seasonality and trend from the customer trained data for CNN models and remove the seasonality from the SKU data set for CNN models. This was done based on indications of an ADF test, which essentially just determines if the seasonality and trend of a specific data set is statistically significant or not. And CNN models don't really deal with statistically significant seasonality and trend very well, so they were removed prior to training. For CNN models, the train data was also normalized and standardized prior to training. This is just a standard practice with machine learning models. So here's the customer train and test data after it was modified to account for COVID. You can see why the ADF test would have picked up on that statistically significant seasonality and trend. This graphic is prior to taking all of those things out, just to have a look at what the data looks like. And here's the same thing for the SKU train and test data. And you can see that there is some seasonality here, but there's not really a significant trend, and that is what the ADF test picked up on here as well. So the data was also split into 3 different structures. The first structure was, it included all of the variables that were pulled from the database, as well as that extended sales dollars summed for all of the customers. And the same thing was done for SKUs. These graphics are just for customers. The second structure broke out the summation of the extended sales dollars into a separate variable for each customer. That will allow the model to take into account if certain customers have greater weight in terms of what the overall sales will be, or if certain customers don't really matter too much to what the overall sales will be. So that was a good way to account for that. And then the third data structure is just a combination of those two. So it uses all of the numerical variables that were pulled plus each customer SKU broken out as its own variable. So because the seasonal component of the data and the use of several variables, the ARIMA model actually became a Starmax model, a seasonal ARIMA with exogenous variables. So all parameters were tested using Python iter tools and stats models packages, and the parameters resulting in the lowest AIC score were selected. The AIC essentially just estimates prediction error and assesses the quality of the model based on certain parameters. And the lower the AIC value, the better the model fit will be. So then the code was run for each data structure for both customers and SKUs, and the results were recorded. For the CNN analysis, the train set was detrended using a linear regression model, and then it was deseasonalized by subtracting from each value the value from the same month of the previous year. And then it was standardized using scalar and preprocessing standard scalar, and normalized using scalar and preprocessing min-max scalar. And then finally, the multi-step, multi-channel CNN model was created using the Keras package of Python. Multi-step is referring to the fact that this project is predicting several months of sales, and then multi-channel just refers to the way that each of the variables is pushed through the model. Another thing to note is that due to the nature of the model, a different prediction is created each time it's run. This is because the CNN model is stochastic, which means there's a certain level of randomness involved. And this makes sense if we think about the fact that it's structured kind of like the human brain. So humans, for example, can look at the same data on several different occasions and come to several different conclusions. So because of this, the model was run 10 times for each data structure for customers and SKUs, and then the average scores for each of the 10 runs was recorded. On to the results. So the performance was assessed using these 3 performance measures. The first one is the root mean squared error, and you can see the equations all listed out here. And then we have the mean absolute error, which is called MAE, and then the mean absolute percentage error, which is usually referred to as the MAPE score. One thing to note about the RMSE and the MAE scores is that they are relative to the range of the data set. So they can't really be used to compare models that use different data sets, but you can use them to compare models that use the same data set. But the MAPE score, on the other hand, can be used to compare any models, no matter what data is used. So here's all of the performance scores listed out for all of the model types with customers and SKUs with each data structure. And then the Starmax models also have that AIC score listed there and the parameters that are associated with that AIC score. So if we look at these performance measures, we can gather that the Starmax model outperformed the CNN model in almost all instances, except for this one here with the first data structure for SKUs. And again, that first data structure is just those original variables that were pulled. So it has far fewer variables than the other 2 models. This one here, the Starmax, performed much worse than the comparable CNN model. And that's not super surprising given the high AIC score there. Between customers and SKUs, customers seem to perform a little bit better. It would be interesting to see if that difference is actually statistically significant or not. But since this project was just really comparing the Starmax versus the CNN, it wasn't really necessary, but it would be interesting to look into that as well. Out of all the data structures, data structure 2 seemed to perform the best, although data structure 3 was also pretty close. So it would also be interesting to see if that difference there is statistically significant. Here's a comparison of the test and prediction points for the most accurate customer Starmax model. This one had a MAPE score of 2.318, and it used structure 2, which had all the customers broken out into its own sales variable. We can see here, this is a pretty good model. The test data is in the orange there, and then the prediction is the green dotted line. So in comparison, here is the test versus the prediction points for the most accurate customer CNN model. This one had a MAPE score of 12.056%, which is quite a bit higher than the last one, which makes sense given what we're seeing in the graph. This was interesting because it is the only best performing model that used the first structure, which is those original 5 to 7 variables. So yeah, just another interesting thing to note with the structures there. This graph shows the most accurate SKU Starmax model. This one had a MAPE score of 2.869, which is a little bit higher than the customer Starmax. And you can visually looking at it, there is a little bit more error there that we can see. This model used structure 3, which is that hybrid structure between structures 1 and 2. So it has them out of all of the structures, it has the most variables. And then in comparison with that, this is the SKU CNN model. This one has a MAPE score of 12.313%, and it used structure 2. But as we can see there, the prediction starts to diverge from the test data at about 6 to 7 months. So it wouldn't, this one probably wouldn't be a very great one to use for practical purposes. To the conclusions. So this can be broken into 2 sections. We can derive meaning from the data that was used, and then later on we'll talk about the meaning of the models themselves. So for the data, results suggest that the COVID-19 pandemic may have had some effect on the forecast, even with the modifications conducted during data pre-processing. There's not really a solid way to determine if this was actually because of COVID or if there would have just been a regular dip in sales there anyway. But looking at this trend for the SKU data, it's pretty flat for most of the train section, and then there's this pretty steep downward trend, and then we're just starting to get a little bit of an upward trend again before we hit the train data. So I'm thinking that probably just how the train data versus the test data was split maybe wasn't ideal given that dip there with COVID. So in the next couple of years or so, perhaps we won't see so much of an effect with that. Perhaps a longer time series could also benefit CNN models, just because you'd get a greater view of what's happening over a longer period of time. And literature shows that 5 years of data is typically sufficient for forecasting sales. However, most of those studies use daily or weekly sales, where this project was aggregated by months, so there were significantly fewer data points. So I'm thinking that adding more data in could see a significant benefit. And then one other thing is that incorporating categorical variables could increase performance. Literature shows that adding region specifically can increase the performance and have a pretty good effect on that. So that would be something to consider. Onto the meaning of the models. Starmax tends to be more reactive to differences in data structures and variables than CNN. All the CNN models, we were seeing MAPE scores around 12%. And with Starmax, it ranged from 2% to 23%. So that's interesting to note. I'm not quite sure if that's just something with the nature of the models themselves, or if it's because the Starmax models were optimized with their parameters. CNN has parameters that can technically be optimized, but there's not really a systematic way of doing it. It's more of a guess and check operation. And there are an infinite number of variables there. So it's a little bit harder to come to a solid conclusion. The prediction window could also be decreased to 3 to 6 months for the CNN models. As we saw in that one graph before with the skew CNN model, the prediction started to diverge from the test data at about 6 to 7 months. So I think that it would be better to maybe predict a smaller period of time. This project only looked at pooled analyses for Starmax and CNN models, but in the future, those could be compared to individual analyses. I could see some practical applications there if a company wanted to just predict for one specific customer or one specific SKU. And I don't think that a lot of other studies have looked into that previously, so it would be an interesting thing to consider. Many other studies have found success using hybrid models as well to forecast sales, and those hybrid models typically outperform the individual models because they can take into account the most beneficial aspects of 2 or more models and kind of customize it more to the data that's being used. Or other machine learning models could be tested. There are a ton of different other neural network models. There's random forest, things like that. So using one of those for the customers and SKUs could potentially result in better performance than the CNN model or maybe even the Starmax model. So which model is best for use by company A at this point in time? The results show that Starmax performs better than CNN. Given all of the variables that were dealt with in this project. They return smaller RSE, MAE, and MAPE values in almost all circumstances except for that skew models with the first structures. CNN actually performed better, but that seemed to be an anomaly. Starmax is also much easier to use and understand, which makes it the optimal forecast modeling option for company A, and probably lots of other companies that may not necessarily have the resources to put a bunch of time and effort into developing a machine learning model that is geared toward their data and is optimized. So removing the limitations that were discussed previously could lead to different results, but at this point in time, it's probably best to move forward with Starmax for company A because it performs well while also being relatively easy to use when compared with more complex models such as CNN. So here are my references. And thank you. Does anyone have any questions?
Thank you, Sarah. Yeah, and just open it up for any questions. I know we're running down on time a little bit here, but if anyone has any questions, please feel free to unmute yourself and ask Sarah.
I have a question.
Mm-hmm.
So how did you determine the effect of COVID-19 on the data that you replaced?
Yeah, I essentially just looked at, I'll bring out these graphs here. I just looked at this here before it was switched, before the values were modified. This was after the values were modified, but I looked at the original one. And there was like right in here, there it was literally like so far down, and just from conversations with the company as well, it was determined that that was the case. It was very rare for that to occur. So for customers, it ended up being April through August, and then apparently the SKUs that were chosen seemed to be ones that were harder hit by COVID. So that extended all the way to December 2020.
Thank you. Other questions for Sarah?
Nice job, Sarah. It's really interesting. I had a question about, were you able to tell, and maybe this is outside the scope of the project because you tackled a lot, but which parameters ended up being used by the models, like out of all the different variables in your structure?
Yeah.
Were there similar ones between SARIMAX and CNN, or did it pick different parameters that were more predictive than others?
Gotcha. Yeah, so the CNN model does not have the same parameters as the SARIMAX. It has like batch size and pooling layer and things like that that are a little bit different. The SARIMAX parameters are just like the level of differencing and the seasonal component. So those can be more you can run through a series of them and figure out which one is going to be the best, but that's not really the same with CNN. So I do have the SARIMAX parameters listed here. They were all different for all the different data structures and data sets, which I found interesting. I guess I maybe would have expected some of them to have similar parameters, but they're all different. So.
Thank you. And how about, like looking back at the data structure, you had a lot of different variables related to the customer, I thought, or the SKU. So did you end up incorporating all those, or is it just looking at past sales values versus like to predict the future sales values?
Oh, I see. Yeah. So the structure one took into account these original ones, and then for SKUs, it had those two additional variables there as well. But then structure two was the only one that only looked at sales. So the sum and then broken out by all the customers and or SKUs. And then the third data structure also included all of these ones.
Okay.
Was that what you were asking?
Yeah, I was trying to understand if it was taking into account how those other variables performed over the same time period to predict the sales, like relationship, like were they predictive of sales or not?
Yes, these variables are all predictive of sales, and they were with data structures 1 and 3, they were taken into account for the models, but they don't give you like an estimate of what weight each variable has.
Okay.
Yeah.
Kind of was good. Okay, thank you.
So we might have time for a couple, maybe 2 quick questions for Sarah and a brief response, or just so we can keep going with our schedule. But Sarah, I might ask this. You alluded to some of the regional impacts, you know, some of these of the different sales in the different regions. Would you anticipate that the model that was the SARIMAX would be comparable to be able to predict on more regional levels, or could CNN be another opportunity to explore at a different level?
Yeah. With including region, if I were going further with this, I would probably, instead of using random selection out of all customers, I would probably narrow it down to a region and then randomly select customers from that region. I think that might result in better pooled analyses for CNN. And yeah, I think I had mentioned that the literature shows that region is one of the categorical variables that can have the most impact on the outcome.
Thank you. time for maybe one more quick question, if anybody does have one.
Yeah, really great project here, Sarah. Thanks for walking us through it. I'm curious more broadly how a company incorporates the sales forecasting data into strategy, and sort of how this data could flow into an existing organization.
Yeah, it is interesting because even if a model has good performance and it's pretty accurate, anything that changes within the day-to-day operations is going to actually change the outcome. So whenever you make a prediction and then companies use that prediction to act, then the prediction will change. So it's kind of an interesting concept, but generally speaking, companies will use the prediction to determine potentially like which customers or groups of customers they need to put more of their resources into, because they're hoping for more sales than what is predicted, or for SKUs, it can help with how to determine what you're going to price those SKUs at, and different things like that. So there are a lot of different applications within daily operations for sure.
Hey, thanks.
All right, and if anybody has any comments or suggestions, you may email those either to Sarah or to myself, and we can work to get those other commentary items back to her there. So Sarah, thank you very much. And on behalf of all of us there, congratulations to you. And see a few people have their hands clapping out there. So congratulations to you. It was quite a journey so far. And while we're not done, it gives us some hope moving forward here. So a wonderful job on sharing your project and topic with us all here this evening. So thank you very much, Sarah. Okay, let's see. Next up, I wanted to introduce and welcome Per Lundmark, and Per's topic relates to that of remote sensing in forest carbon. So a study of carbon sequestration opportunities to that end within a study area in southern Minnesota. And so with that, Per, I will stop my share here and have you screen share out, and go ahead and begin when you are ready, Per. Thank you.
Great, thank you, John. Good evening, everyone. Thanks for coming and listening to some of our projects here. Well, so I've spent the last few months working to understand how remote sensing can be used for the benefit of forestry carbon sequestration projects, focusing on the Whitewater Valley in southeast Minnesota, and happy to share my findings with everyone here today. I'll begin with a background on the current science, provide an overview of my study area, walk through methods which included LiDAR and forestry inventory data processed through a random forest classification machine learning model, go through my results, and comment on some of the limitations, conclusions, and areas of further study. So let's hop right in here, current science and the study area. I used the Whitewater Valley in Minnesota as a study area to identify opportunities for remote sensing carbon stock through use of LiDAR and validating that out through some field collected data as well. This data was analyzed in ArcGIS Pro using random forest classification tool. And through comparisons of these data sets, trends can be identified to benefit deployment of these carbon sequestration projects. It's important to study since the ability to quantify and track progress of forestry carbon projects is essential as they're deployed globally to sequester atmospheric carbon and lessen impacts of climate change. So a little background here. There are a few different formats that forest ecosystems use to store carbon. And we're all familiar with the concept of plants absorbing CO2, we breathe it out. they absorb it, but where exactly does it go? And the tree is perhaps the most intuitive format. So, the tree, as Birdsey et al. Defines it, is anything defined as above or below ground portion or of live or dead trees. So we have our tree there. We also have understory vegetation, so you can see little shrub or fern on the forest floor. Also have our soil, and so that's defined as anything organic matter down to 1 meter. And finally, the forest floor, and so that's all of the dead organic matter moves up on top of the soil there. And it's estimated that ecosystems similar to the Whitewater Valley could contain up to 200 metric tons per hectare as an estimation for storage of forest carbon. So this is sort of the scene that we find ourselves in down in the Whitewater Valley there as well. Extensive research has been conducted on the above ground content of trees. So here we have a graphic borrowed from the U of M forestry website, which uses data from a US Forest Service study on trees which are generally present in Minnesota. You can see here oaks, some familiar species on there. And generally we see an increased trend of above ground carbon as the diameter at breast height increases. It's roughly some sort of geometric pattern there with lots of carbon being added as the diameter of breast height DBH increases there. So the Whitewater Valley, and there's my study area, and it was selected in part due to its location within an opportunity zone for reforestation as defined by the Nature Conservancy. You can see the map over here on the right side of the slide here, areas in green identified as opportunity zones. And this tool was built as part of a conservancy initiative, which considered a few different variables: biophysical suitability, land cover type, ownership, soil condition, that were favorable for reforestation projects, for carbon sequestration projects. And the Whitewater Valley is forested, or is located within the greater opportunity zone and exists as an existing forest plot that was favorable for studying. And so by studying the forest in the Whitewater Valley, we can get some insights to be gained on how remote sensing could benefit projects in the greater opportunity zone throughout the Southeast. You can even see here the Whitewater Valley is kind of carved out. It's really small down there, but the Whitewater Valley theoretically excluded from the opportunity zone, but exists as a good model for the greater area. And the Whitewater Valley as the unit includes the Whitewater Valley State Park, the main portion of the wildlife management area, and then the north and the south branch. It's about 11,000 hectares, somewhat contiguous. You can see there's a little bit of a division here, contiguous land, and follows the Whitewater River as it flows into the Mississippi. A little more information on the Whitewater Valley. So we have some land cover statistics which show a majority of the valley is forested with other land cover types present in smaller proportions. And it's really these forested portions that are of interest to the study. Although it should be noted that other land cover types can be effective at sequestering carbon as well. But we'll just focus on the forested portions. Given that the valley is within the wildlife management area, the forests are relatively free of disturbance, but they are maintained to promote habitat through prescribed burns, maintenance of forest openings, and things like that. Also included is a photo from the South Branch unit taken this spring. Fishing trip I took with my dad. I think it does a good job of sort of setting the scene of the bluff country if you haven't been down there before. River down in the lower valleys with the bluffs rising and forested portions up there. I think on this day it was cold and snowing when we went in, and we were in t-shirts on our way out. So we have a variety of conditions down there. A little more information on the actual forest in the valley there. So of the forested areas, a majority of them are oak. And if we recall, oak do a good job of sequestering carbon as they grow, and other deciduous trees present in here as well that are also effective at storing forest carbon. Here's a picture of a little bit of a warmer day. It's nice and green after a rainstorm come through. Great. So moving along to the methods. And when I was putting together the study, I noticed three primary components that were consistent across other similar studies. So these included a baseline carbon stock measurement, so what we're working with on the ground, use of a LiDAR data set to input into some sort of machine learning model, being random forest classification being one of the most common ones. And so it seems with advancements in both LiDAR and machine learning, the academic community sees a benefit in sort of this general framework for exploring forest carbon. So almost immediately I hit a speed bump with no readily available baseline available online for the Whitewater Valley. Absence of any major carbon projects, and some of the DNR initiatives are still in their early stages. So nothing was available immediately for deployment as a baseline. So I went searching for maybe some other data that could be used as a baseline and help build out the study. I narrowed in on a few relevant data sets, including LiDAR data collected in 2008 through a DNR initiative. And its original intent was to document flooding extent as part of a FEMA relief package. But fortunately, it was available online through MN Topo, and was able to be used for the forestry project as well here. It has accuracies of 0.4 meters horizontally and 0.36 meters vertically. And that really fulfilled one of the three components I saw in the relevant studies, but the baseline issue still remained. I found some inventory data available through the DNR, which was collected over a number of decades and included relevant measurements for carbon storage, like species type, density, size, and was collected over field studies over this period of time. And it seemed plausible that this information could be combined with above ground biomass data to create a baseline of sorts to compare the LiDAR data against. I also pulled some DNR land cover data that was collected using imagery and field surveys in 2008 and 2009. And it seemed that once kind of like this forest inventory management, that through these two data sets, perhaps some sort of baseline could be used if combined with some of the research done on above ground forest carbon storage. And so kind of working through these data sets, I had come across some research from a researcher in Minnesota, David Wilson, and contacted him to try to kind of get down to the understand, could these components be used to create a baseline for my study here? I was a little skeptical given the time range. You can see it was almost over 4 decades of data collection in my plot. So some of the data was from the mid-90s, right next to something from 2012. And David Wilson, my subject matter expert, proved this out. He said, FIM data, that's our forest inventory management data, couldn't accurately be deployed to estimate a carbon stock baseline. So I was really fortunate to come across David's work. He's a St. Mary's Resource Analytics graduate or alum, and he forwarded me some of his research that helped kind of put together a new vision for what that baseline would be, and some of his projects working with LiDAR to establish some of these carbon stock baselines. So as a result, I moved along with using LiDAR to establish a carbon stock baseline. And so kind of the big picture is we take our non-ground returns, subtract our ground returns, and knowing from what we know from some of the studies on forest carbon storage, there we have the tree, which is storing biomass, which is storing carbon. So there are some limitations on this technique, which will be discussed later, but it was a really clean way to develop a baseline. And although it should be noticed that this doesn't specifically quantify carbon, but it can be used as a tool for identifying areas of increased forest carbon. And as we recall from our graphic here, as we get bigger trees, we're going to have more carbon. So the baseline layer was created at hectare scale and really represented a map of above ground biomass modeled after David Wilson and his team and some of those studies that they had been working on in northern Minnesota. And from here you could see the process represented by a flow chart where LiDAR data was used to develop a biomass baseline here. And attributes from the rest of the LiDAR data set was also incorporated, converted into rasters representing different characteristics of the LiDAR point layer. And we count, elevation range, and intensity. And I also pulled upon some of the DNR land cover and FIM files for features relevant to carbon stock, land cover type, species, size class, density, and the cover type from some of the FIM data as well. And these files were combined and summarized into what I called an analysis points layer, and the purpose of which was to simplify input into the random forest classification tool. Here we have a representation of the carbon baseline map, where biomass is represented as a height in meters and cell size of 1 hectare. You can see down at the scale there, 30-meter trees being the upper limits of what one would expect a tree in this area to grow. And upon general visual inspection, you can see the floodplain, kind of the lower areas of the valley are represented on there, where biomass is generally lower than up in the hillsides. And the various data layers were then summarized into the analysis points layer using my linear interpolation method. And this was chosen as the best method considering the many pockets and edge territories of the area. As you can see on the left, land cover and point count layers represent many pockets of different values for the model to interpret. And the analysis layer is pictured on the right with a table including the variables and the points just for reference for ease of sort of visualizing how these layers were all put together. And each of the points included attributes from the various input tables and was run through the random forest classifier. Over to our results of the random forest classification. And here we have our prediction map. And the prediction map produced a similar visual to the baseline. You can see, once again, lighter areas in the valley representing lower biomass height and more biomass, sort of in the forested areas up in the bluffs there. Note the lower maximum value of the biomass height of 21 as compared to 30 in the baseline map. And in order to more comprehensively compare the prediction map to the baseline model, geographically weighted regression was conducted with a result of 0.84 R squared when compared to the carbon baseline map. That was really seen as the best way to quantify the accuracy of the prediction map when compared to the baseline. And here we have the GWR, geographic weighted regression results, represented in a scatter plot with a general positive linear relationship with a few of those outliers. Although, generally I was pleased with the R squared of 0.85, meaning 0.85 of, or meaning 85% of the data was explained by the model. There's some important caveats that I'll go through in the discussion section. And also along those lines, really the purpose of the study was to look at the opportunities for the different data sets and how that works with remote sensing. And so I thought it was important to look a little deeper at the data. And fortunately, the random forest classifier does a really good job of spitting out these variable important tables here. And so understanding the value of the different input variables is really central to the study. And you can see the importance column contains the number of times a variable was used in a decision tree in the random forest model. And the percentage column there being the corresponding percentage of total decisions where the variable was used. And note the high importance of the LiDAR derived data. We have our elevation, intensity, and point count all coming from the LiDAR data. And conversely, lower importance for some of the DNR collected, either the FIM data or the DNR land cover data there. And again, considering this study was more looking at some of the inputs, I think it's really good in the discussion here to move into understanding how those different inputs affected the output here, rather than just focusing on the model accuracy. And so I think this graphic helps represent, a process I did with just general visual analysis of trends apparent to the human eye here. And, you can see from the prediction layer here represented on the left, this is overlaid with the aerial image here with a bit of opacity for us to be able to see better. You can kind of see some of the darker areas are the forested. Maybe this oak savanna down here is a little bit lighter, and down in the main area of the floodplain, it's represented with lower biomass, and you can see that represented with the lighter squares down over here. And so, although the hectare scale is pretty coarse, you can kind of pick up on some of these trends that were apparent in the data in the prediction layer there. And kind of back to the original question of, could I use some of this forest inventory management data, and what variables really contributed to an accurate prediction layer? And so if we're to believe that the LiDAR base map does accurately represent carbon stock, as described by Wilson et al. In their studies, conversely, then we can turn that on its head and say, well, if we think this forest inventory management data, or FIM data, is inaccurate, we can really prove that out and see that in the results in our classifier model. And so recall that the forest inventory management data was collected over a number of decades, almost 4 decades. So we might have data from 96 right next to data from 2015 in kind of a patchwork. And, it's definitely possible that this resulting FIM data is valuable in the model, but we can see it's probably not as highly important as the LiDAR. You can see density class in the FIM data being the most important, which makes sense. More density, more biomass, more carbon stock, likewise with species, size, cover type, things like that. And it's possible that the categorical variables like cover type for the FIM or the DNR cover type are coming in at the bottom because there's not a lot of importance or a lot of differentiation across the study area for some of those variables on there. And so overall, I think it's also important to understand is the model biased towards LiDAR data, because that was what was fed through in some of the training there. Considering the base map was LiDAR, LiDAR derived on there. So, I'm inclined to see as the low importance of the FIM data to be resulting in the patchwork nature of the data set, just like David Wilson had said, that it wouldn't be a very reliable, accurate data set. So bias of model limitations, bias of model towards LiDAR derived variables. I think it's, something to be considered if it were to be used in other areas. I think it's also important to understand the limitation of the LiDAR data set itself, with lower accuracies and improvements in LiDAR more recently, that perhaps it could benefit from some high resolution LiDAR. It's also important to consider the LiDAR was collected in November, which is probably a good time of year. You get some good trunk returns with the leaves off of trees, but we could have some compounding variables with something like oaks kind of hanging onto their leaves longer than other trees, could artificially inflate some of the counts on that data later. And finally, I was really pushing the limit with running some of these analyses through Pro. So I think potential with working with higher resolution data sets would benefit with running directly through a Python script. A sort of mystery limitation here is a missing portion within the state park. I went through a few troubleshooting attempts to try and get the prediction layer here to recognize and to build in some predictions in the state park there. And so that's definitely affecting some of those results in my regression model and things like that to prove out the accuracy. The state park is 826 hectares, and we do have some data represented within it. So, potentially missing 800 points on a data set of 11,000 points, could definitely introduce some bias to the model. However, the park does have similar features to the rest of the study area. So we could assume that it would fit in with some of the trends in the rest of the area. Some of the opportunities to improve to incorporate some of the ground truth data to quantify variables in a traditional method, something like an updated timber survey or applying an official carbon forestry protocol like the American Carbon Reserve Forestry Protocol, would represent a better way to develop a ground truth baseline, and would require field collection similar to a timber study, something like that. Also considering that there's a lot of carbon stored in soils, it would probably be important to also include that in the study as well. As you can see here, the graphic adapted from Birdsey et al. Study, almost 70% of forest carbon is stored in the soils. And we have seen some studies that have success using imagery data like Landsat to identify and recognize soil carbon, and the Angel study being one of the more recent ones on there, and using some spot satellite data. As high resolution LiDAR imagery proliferates, I think there could be some opportunities for enhanced classification potential. I've seen some studies that show individual tree identification may be realistic, could lend itself to something like year-over-year growth tracking, resulting in really highly accurate carbon stock quantification. Other more regular collection frequencies that potentially could be deployed through satellite LiDAR collection would also benefit the study. Currently, NASA and some other initiatives have been launching LiDAR satellites for those types of data collections. And Minnesota is also deploying a high-resolution LiDAR collection through the 3D GEO initiative, and actually recently collected data from my study area within the Whitewater Valley. And the data is currently in the review process, so I wasn't able to view it, but that would be could benefit the comparing either the 2008 data to the more recently collected 2022. I think there's a lot of potential for opportunities in that area. And conclusions, low resolution LiDAR can be used as a general indicator for carbon stock estimation, and could be valuable for validation of other quantification methods, or as an option when lower computing power or limits the ability to work with more massive data sets. And as remote sensing improves, it will remain valuable to incorporate ground truth data into analyses to understand how the remote sensing data compares. You can either use it to truth out the remote sense, or be able to use the remote sense to compare against the field collected data, in sort of a system of checks to get the best result possible. And it kind of used the study to dictate that. I think like any tool, remote sensing data has its limits, and it's important we understand those limits and incorporate other tools as we see necessary. And more broadly, I think it's important to understand land use change implications for research like this. If we recall, the Conservancy study identified generally the whole southeast of Minnesota as an opportunity for reforestation. And I think that doesn't do service to the existing land stewardship and existing economy based around farming in that region, and recognizing the ecosystem services and potentially carbon sequestration that those land stewards are having on the land right now. And with that, I think I'll thanks everyone for making the presentation here tonight, and we'll open to questions here.
Thank you, Per. Any questions that anyone may have for Per? Feel free to ask away here.
Thanks, Per. Really interesting work. And I was curious about the variable importance, and you mentioned elevation was the most important. Is that the elevation, like the ground elevation above sea level, or is that the elevation difference between the canopy and the ground?
Yeah, good question. Yeah, these variables were input just with the raw LiDAR data. So that is an average of all elevation of all points in that hectare cell. Yeah. Yeah. So I think, I think one of the limitations of the model, like I was saying, with its, bias towards the LiDAR data, I think it could easily just find those elevation ranges of those bluff sides, right? And build in a prediction and say, well, if it's between the river bottom and the bluff top, then it's trees, which isn't a bad thing. I mean, it's doing its job, but I don't know if it'd be scalable to other areas.
Right. Yeah, I was wondering, picturing that study area about slope, and if that would be a predictor at all. Like thinking about the hillsides having a steeper slope than maybe the water, like the river areas, but but there's trees on the flatlands too, so maybe not.
That's right. That's right. Yeah. Yeah, no, appreciate it.
Other questions for Per?
Yes, I have a question for Per. I apologize, I had to step away for a second. So if this question has been answered, I apologize. But what led you to decide to use tree cover as opposed to like native grasslands by chance?
Oh, that's a great question. The easy, simple answer is trees stay put year over year and make for a really good study topic, for a student. There's a lot of great research, like I said, with using satellite imagery in some of these areas. But the thing that's hard about pulling data from a satellite image is that you might not be able to find supporting data around that same time period. I was fortunate to have that LiDAR data. Let's see if I can zoom back here. That sort of matched up with some of my other data sets here, right? We have our land cover data collected 2007, 2008, LiDAR 2008. The trees aren't going to change that much, over time, unless there's some sort of disturbance regime or something like that. Did that answer your question, Jerry?
Yes, thank you.
Other questions for Per? Per, I understand your topic and working with you for quite a long time on this, but and I know you've alluded to it a little bit in here, if you were to anticipate what other potential researchers could, I guess, look at as potential limitations or liabilities, and I understand that we all do, that there's no data set that is perfect, and technology can also be a subset in or above that. But what would be some critical limitations that you could see other people, other researchers going at in your work that you shared here today, and what would your response be to those?
I think if I understand the question correctly, I think the limitations on the model would probably be the main area to attack. I think it is easy for complex systems, for researchers like us to want to take complex systems and distill them down to, sort of one number. I can get 85% of the area explained with my model on there. And I think being curious about what those inputs are doing and how those inputs are behaving and performing really shows what you're getting out on the other end with the model. Like Greta had asked, kind of what is it actually looking at? It's probably, maybe just look at elevation and saying, well, if it's high up, there's trees there. But can we feed in more data to say, nope, there's definitely trees here because these certain conditions exist, and improving that out and being open about some of those variables. I think for me as a student, there were a few speed bumps, and John, I came to you on it and I said, well, they're not saying what these variables are doing in their model. They are saying, here's our result, here we're moving on, and here's what more people can do, or people can do next, with the further study. And they build off that. They have a familiarity with their data inputs, so we just have to trust them. But yeah, I think it's important to look at those input variables.
And ultimately, where we're going with this is that sometimes there is not the limitations of our output are as good as what we have. Typically, that's either the technology to derive the data, which in your case, is a big one, or field visits, things like that. We can't do everything just with time, resource limitations. But coming back full picture, it's exploring those limitations, exploring those parameters, exploring the inputs to see what really can happen. And if we needed to create a different scale, we would have a better understanding of saying, okay, this parameter can alter X, Y, and Z, or this one is altering A, B, and C at scalable levels. So it's really the root of what we do a lot in Capstone is exploring. For us, learning is the paramount goal, but exploring those inputs and learning from those.
Right. Yeah, opportunities, and that was
Yeah.
central to what I was working on. Mm-hmm.
So Per, on behalf of all of us in attendance here, we'd like to congratulate you as well on a very robust and interesting Capstone project here as well. And I know we're not yet at the final finish line, but again, the purpose of all of our presentations here to solicit feedback. And like Sarah and with our other presenters, if anyone has any feedback for Per, you may reach Per or send them to me as well and let him know what your thoughts and or ideas might be to help him improve. But Per, there are a litany of different clapping things going on there for you there from our group in attendance here. So Per, congratulations to you. We appreciate all of your energies as well. So with that, I'll go ahead and pause the recording. We'll take a short break and be back here. Well, it doesn't seem like too long here. Take a few minutes, stretch break, and we'll be back here in maybe 5 minutes and finish up our presentations with Annika and Ian here this evening. So thank you, everyone. All right, so welcome back, everyone. And as soon as I can get my window out of the way here, we will begin. There we go. So welcome, folks. We'll continue our Capstone, our DIGA694 Capstone presentations here this evening. Again, just a reminder that our session here is recorded so that people can go back and rewatch or pick up anything that you may have missed the first time through joining us live here this evening. So joining us next will be Annika Freight. Annika is analyzing the SARS-CoV vaccination sites in a case study of Duluth, Minnesota. And so with that, Annika, we'll be excited to hear your work, and go ahead and assume the screen share there. And we look forward to hearing all about your project. So Annika, we'll turn it over to you.
Okie dokie, can you all hear me and see my screen?
Yep, we can.
Well, so my project is called Analyzing Prudent SARS-CoV-2 or COVID-19 Vaccination Sites, a case study of Duluth, Minnesota. And you'll note also that there's no R in my last name. It's fate. So just quick table of contents. First, I'll provide some background information and explain the introduction to the problem a little bit. And next, I'll step through the methodology and talk through some of the data that I used for analysis. And finally, I'll discuss the results of the analyzed output locations with you all. So I think it's safe to assume that we all know someone who has COVID or perhaps had it themselves. Basically, having readily available vaccines will hasten herd immunity and reduce the number of unfortunate infection outcomes for people who get COVID-19, i.e. long COVID that we're hearing about a lot, and deaths as well. There are a handful of community vaccination sites in Minnesota that allow residents to safely and efficiently receive the COVID-19 vaccination sequence at no cost to them and are in a familiar setting. As I said, there are a handful of these community vaccination sites in the state, but there are none outside the 7-county metro or the Twin Cities area in Minnesota. So I am specifically looking at Duluth in this case. Why Duluth? Well, Duluth is an important port city and is a popular stop for recreationists, both domestic and those seeking international passage to Canada. The area known as the Duluth Metropolitan Statistical Area consists of Duluth as well as cities and townships like Superior, Wisconsin, and 2 harbors. Almost 300,000 people live in this metropolitan statistical area, of which more than 2/3 live within Duluth or within 30 miles of Duluth. And also Duluth is one of the CDC's 500 cities for which there's ample data describing health outcomes, which I will discuss shortly. So COVID-19 has caused many deaths and otherwise undesirable outcomes. At the time of this presentation, there have been upwards of 1 million deaths in the nation from COVID-19, and in Minnesota approaching 13,000 deaths. But some people are at more risk of severe infection outcomes than others. And what I wanted to know was what demographic considerations should be considered when thinking about placing a new vaccination clinic so it serves those who need it best. And through my literature review, I discovered that there are 3 key factors that contribute to increased infection outcomes. And the first is presence of an underlying chronic disease. Those with chronic diseases are more likely to have poor infection outcomes and have illnesses that last longer when infected with COVID-19, specifically chronic kidney disease, chronic obstructive pulmonary disease, and diabetes could explain as much as 24 to 45% of health complications from COVID-19 infection. In addition to the presence of chronic disease, those 65 and older are more at risk for a longer illness or adverse infection outcomes, as well as living in group quarters such as nursing homes or dormitories, put you at risk for a rougher infection, not just because of the age of the people who live there, but also because you're in close quarters with other residents and doctors and staff. So in this project, 3 potential vaccine clinic sites are identified based on their proximity to an area with high chronic disease, high elderly population, and within a 1-mile radius around nursing homes in the study area. And the data I used to elucidate these sites was all based on the 2010 census, both chronic disease data and age bracket demographic information. So first, I pulled census data that described age brackets in the study area from Esri's Community Analyst web app for tracks in Duluth, Minnesota. And in this case, those aged 65 and older are what are considered elderly. And then next, I pulled data from the Centers for Disease Control describing the crude prevalence of chronic kidney disease, chronic obstructive pulmonary disease, and diabetes for tracts in the same study area in Duluth. And crude prevalence is defined as the number of cases in a tract, in this case, divided by the total population of the tract. And third, I identified nursing homes in the study area via information from a third-party website and made a point layer of those in ArcGIS Pro. So I wanted to visualize the population of those age 65 and older by census tract, as well as visualize crude prevalence of chronic disease by census tract, as well as run an optimized hotspot analysis for the prevalence of each chronic disease, and finally establish a 1 mile buffer around each nursing home. So ideal vaccination clinic sites are in areas with high chronic disease prevalence, high elderly population, and within the 1 mile buffer of a nursing home. This is just a graphical description of what I just went over. So in the green are the sources for the data, the CDC Places study, Esri Community Analyst, and that third-party website for the nursing homes. The blue boxes display the data that I used. The gray shows the interim steps before I actually did the analysis. And the red, in the case of the chronic disease data, I ran the hotspot analysis. And in the case of the age data, I just visualized the population. And all three of those factors resulted in determination of potential vaccination sites in the study area. So now I'm going to talk a little bit about the data that I used. This is just the extent of the survey area. In the blue outline, each of these polygons is a census tract for which I had data that described the age and chronic disease prevalence. And to get the data from ArcGIS Community Analyst, I was able to ask it to give me a report of the age bracket demographic information for each of these census tracts. So the output looked something like this. And I've highlighted this here for you to see that this is the measure that I used, the age 65 plus, the total population from the 2010 census. And I had something like this for every census tract. Moving forward to the other data, the chronic disease data came from the Centers for Disease Control's 500 cities study, which reports the prevalence of 20 chronic disease markers, which describe things like presence of arthritis, high blood pressure, number of teeth lost, as well as the 3 chronic diseases that I examined here, which are, again, chronic kidney disease, chronic obstructive pulmonary disease, and diabetes. And it's called the 500 Cities Project because it provides measures for the nation's largest 500 cities, of which Duluth, Minnesota is one. And finally, for that nursing home data, I just used a third-party website called the Local Network, which aims to provide transparency for researching things such as nursing homes. And all I did in that case was take the addresses of all the nursing homes in St. Louis County, Minnesota, put them into ArcGIS to make a point layer, and then I truncated the county data set just to the study area. So all that was left were the nursing homes in the study area of Duluth. So initially, the age data and the chronic disease data that I pulled from those sources were associated with the census tract, but in name only, not spatially. So what I had to do was download a shapefile of census tracts as drawn in the 2010 census from the Minnesota Geospatial Commons and join them to the data describing the chronic disease and the ages. So the join field that I used was the census tract. And ultimately I ended up with data that described the age of those 65 and older, the crude prevalence of COPD, diabetes, and kidney disease for every census tract. And these two are just the spatial data that allowed it to be drawn on the map. So here are the results. This figure shows the elderly population by graduated colors and also the locations of nursing homes. So the darker green represents the highest population of those 65 and older, and the most age 65 and older in a census tract is 1,689 people. So this census tract would be a good place to put a vaccination clinic. And now for the chronic disease results. This is the first one is the chronic kidney disease hotspots. The software has indicated that there are 2 census tracts that are statistically significant enough to be considered a hotspot, although at a 90% confidence interval. So in this case, this means that placing a vaccine clinic close to or in either of these census tracts would be prudent. And the figure for the diabetes prevalence looks very similar to the last one in that there are no hot or cold spots except for those, the same two actually. So once again, the software has indicated that this is statistically significant, and to put a vaccine clinic here would be prudent as well. And finally, there's the chronic obstructive pulmonary disease hotspot analysis, which is more dramatic and dynamic than the previous two. There's actually a cold spot up here. And in this case, this means that if you were to put a vaccine clinic in the census tract, it would not serve those with chronic diseases as effectively as if you put them down here. The software has indicated that there are 4 census tracts with high COPD surrounded by 2 other hotspots with high COPD, albeit at a lower confidence level for those other 2 hotspots. So to put a vaccine clinic in this area would be prudent, as it would serve those with COPD most effectively. So here is an elucidation of the potential sites. This figure shows, once again, the extent of the census tract study area in blue, the 1 mile buffer around the nursing home locations, and I have indicated 3 potential sites for vaccine clinics based on the factors I just discussed with this yellow triangle, and I will go over each of these sites in context as well. But before I do that, I'd like to reiterate the goal of this project was to identify promising vaccine clinic locations that best serve populations at risk, in this case, the elderly and those with chronic disease. However, analysis revealed that there are no census tracts that have high elderly population and are within chronic disease hotspots. It's either one or the other. So the 3 best potential sites are going to be explained based on their proximity to those populations of need. And you'll note as well, all sites are within the 1 mile buffer around the local nursing home. So this is the first site, potential site A. I have chosen to display this against the age data as well as the COPD prevalence hotspots because that hotspot has the highest confidence interval and it is the most dynamic. So potential site A serves a moderate elderly population. You'll notice not the dark green, not the highest elderly population, but it would serve those with chronic diseases the best because it is in that hotspot that was identified for all 3 chronic diseases, if you recall. So potential site B is located in the census tract with the highest elderly population. However, it is located not near any chronic disease hotspots. So it would serve the elderly population quite well, but not necessarily those with chronic diseases. And finally, potential site C. Potential site C is located in the census tract adjacent to the census tract with the highest elderly population. And you can see it has a somewhat moderate elderly population itself. And once again, like the previous, is not located near any chronic disease hotspots. However, it is close to other nursing homes, not in the buffer of either of these ones on the side, but enough that ARC decided to make it all into one shape. So this potential site would serve residents of these 3 nursing homes quite well. So conclusion, chronic diseases such as chronic kidney disease, COPD, and diabetes can exacerbate complications for those infected with COVID-19 as well. Those who are elderly and or live in group quarters like nursing homes are more at risk for infection. In the study area of Duluth, there are no local areas where chronic disease hotspots and high elderly population overlap. However, it's possible to place vaccine clinics to best assist residents who fall into either of those populations. Looking forward a bit, these methods are applicable to any demographic obtained by the census. So any other age bracket or all age brackets, for example, or any other chronic disease for which there are prevalence values. That CDC 500 cities study has 17 other chronic disease markers that you could use to analyze anything like this. In the future, if I had the chance to, I would like to work in something a bit more concise, such as actual addresses and actual streets, or maybe even work a network analysis in there somewhere, just to result in a more concise placement of a vaccination site. And other variables that could be considered for similar analysis include a nearby presence of healthcare infrastructure. For example, in my literature review, I learned that a really key consideration of establishing a vaccination clinic is its proximity to places where vaccines can be kept, especially the COVID-19 vaccine, which has to be kept at ultra cold, -80 Celsius. Or another variable that could be considered is general population density by census tract, and or presence of public transportation. And that's relevant, especially when you consider like the 1 mile buffer. So taking those into account would be realistic and important when establishing vaccine clinic locations. And that concludes my portion of the presentation, and I'd like to open it up for questions now.
Okay, thank you, Annika. Are there any general or specific questions that anyone in attendance here live tonight might have for Annika? Per?
And a great presentation. I always think public health data is so interesting. Maybe this is like asking a parent to pick their favorite child, but you know, was there anything in those potential sites that would push you towards one or the other? Were those ranked? A being primary, you know, C being, you know, tertiary, or any variables that would maybe push you towards one or another?
So in this case, I more or less weighed all these considerations the same. However, I am inclined to pick potential site A just because it's pretty dramatic in that it would serve all those people with chronic diseases most effectively. Like the hotspot analysis kept throwing up those 2 census tracts as being significant. So I guess if I had to pick a favorite, it would be potential site A.
Thank you, Per.
Yeah, great,
question.
thank you.
Yep. Other thoughts, comments for Annika?
Annika, good job. It was definitely interesting and timely project. I was curious if you know any more about how that disease data is collected or aggregated. Like, I just know with privacy, I'm trying to think if they are actually like, if clinics are reporting that at like a census tract level, or if it's by this zip code, or do you know if any more background on that data, how it comes to be?
I don't think it's reported by health networks or hospitals. I think it was similar to the way the census was conducted, that people just go ask.
Oh, okay.
How many people in your household live with arthritis, or how many people in your household are missing all of their teeth?
Okay. Interesting. Were there any other, besides nursing homes, any other places that you thought about considering as a location where at-risk people would gather? Or...
So I thought a little bit about like halfway homes, I guess, but the problem with that is people don't stay there very long. You know, so I did mention like college dormitories, but I focus specifically on nursing homes because the association of increasing age and like severity of infection is noticeable, and it's not necessarily comparable to like college age people getting sick.
Mm-hmm. All right, thank you.
Annika, one thing that I know we've chatted about for a long time was anything that is, as Ms. Poser was saying, very timely, you know, of and relevant of where we're at and present with health-related illnesses, diseases, things like that. Can you comment a little bit on that journey of literature and or the sparseness of it, or you know, I think there's a lot of places that you could go with what came out or lack thereof of literature to help define a goal or an opportunity there. But can you comment on that process and what that meant to you and just in terms of going through the literature and finding or not finding what you maybe needed in this process?
Yeah, absolutely. So when I started collecting literature for this project, it became apparent that there are very few studies that report on COVID-19 specifically. So I sort of had to extrapolate variables to consider based on other pandemics, namely influenza, and even MERS and Ebola. But John, I believe you suggested to me that I could actually use like government data and white pages for this. So that is what I ended up using more rather than studies, just because we all know how long it takes to get something published. The COVID-19 data just isn't, or studies rather, just aren't there yet.
That's always something to think about in terms of when we're looking for a response. There often isn't that literature showcase developed yet. And so it's hard for us to know, if you were to come back and explore this 3 to 4 or 5 years from now, could that change, or could that impact some of the work that you, or parameters, or some of the decision-making utilities? We don't know, but that's part of the fun of advancing projects and research and studies, that we can get some more opportunities to, I guess, engage in other thoughtful platforms of problem solving. And so I think it's not just Duluth that would have been experiencing this. It would be it's many different areas across the nation, as you suggested. So sometimes the lack of literature almost provides us an opportunity. But it's always nice to have that formative assessment piece in the form of literature to give us that support oftentimes. But kind of where we're at now, it's relevancy versus the literature, and timeliness, and where that all.
It definitely is, yeah.
So wonderful. Other thoughts or comments for Annika?
I'm curious if you saw it all like in literature or white pages or anything that you use, if variables would need to change for this analysis based on what variant is more prevalent at the time, or like going into the future with new variants.
Yeah, so I guess not specifically, I didn't encounter anything like that, just because all these variants are cropping up all the time and everything academic published is so far behind. So I would be interested to know that as well. So I was a biology major in undergrad, and I can tell you that bringing like microbiology into it just makes it so much more complicated. But yeah, that would be interesting to know. I didn't read anything specific about subvariants or variants.
All right, thank you. I think it was Sarah there that asked that question there. Any other thoughts or comments for Annika? Otherwise, if anyone does think of anything, either watching a recording at some point and or live here, please, you may email in those comments, thoughts, ideas, opportunities to me or to Annika for consideration as we round out, again, the closure to the finish line in a month or so here, Annika. So on behalf of us all here, Annika, thank you very much for sharing your labor of love here, as the rest of us have been doing. I know it's been a journey, for you and for all of us here to that end. And so congratulations to you. We're seeing the little hands clapping on the screen for you. I don't know if you can see that. So congratulations to you, Annika. And also, I am sorry, I was in a mental thought of something where I put an R into your last name. So I did know that, but wasn't doing that intentionally.
You're not the first person to have done that, certainly.
Yeah, I'd say a rookie mistake, but I've only been doing this for 20 years. So apologies to you on that. Okay, with that being said, if Annika, you may end your session here, and we will resume or continue rather, that of our next presenter here. And so Ian will get you up and ready to go as I am doing that. wanted to introduce Ian's topic to everyone as he is getting ready here. Ian is finishing up his capstone research in using supervised image classification to identify potential wetland habitats in the North Slope Borough of Alaska. And this has been another wonderful opportunity in our growing and evolving capstone arena of this remote sensing and image classification and machine learning and some of the principles of AI really, and making our lives more efficient and hopefully effective in doing more with the time that we have. And so we're excited to, Ian, to see what you have uncovered in your journey as well here. So Ian, we'll let you screen share out and I'll turn it over to you.
Perfect, thank you. Can everyone see my screen?
Yep, we're all good to go.
Perfect. Well, again, I am Ian Robertson, and my project is using supervised classification to identify wetland habitats in Alaska. For the table of contents, I'm going to start with an introduction, which includes a project background and the explanation of the study area. Then I'm going to move on to my methods, which include the database or the data sets that I use, the training data, and then just a general explanation of what supervised classification is. Then I will move on to my results, which are the results of my classification and the accuracy assessment placed on that classification. And then I will finish with a conclusion, which discusses the results, sources of errors, and then future considerations. So for an introduction to wetlands, they are exactly what they sound like. They are wetlands, but more appropriately, they have to at least have one or more attributes. This either means the land is supported by a dominance of hydrophytes, which is vegetation, for varying periods of time throughout the year. The second is the substrate, which is the underground, contains hydric indicators such as iron deposits that remain saturated throughout different time periods throughout the year. And then thirdly, the substrate does not contain a dominance of soil or is considered non-soil, and it is saturated, variability depending on permafrost depth and other considerations for at least a portion of the year or of the growing season of each year. Included next to it is a photo from my project area, at least an aspect of my project area from the North Slope of Alaska. Just a little further development on wetlands specifically. They provide essential resources, specifically wetland plants are provided for the wildlife that inhabit the North Slope of Alaska, especially those that need both an aquatic and terrestrial terrestrial way of living. They also act as natural deterrents of flooding. They're able to continually be saturated, so it may keep flooding from occurring in the surrounding area. They also act as pollutant filtration. They're able to take pollutants in and filtrate them out so they don't reach other water bodies or perhaps like a farm field, whatever it may be. They are also methane producers, and then finally, they are carbon collectors. Now, the challenges of wetlands in Alaska, there's a multitude of challenges. The biggest being the lack of mapping, actually, which is why I've taken on this project. But only, so 51% of Alaska is considered wetlands, and that is about 40% more than the rest of the lower 48 states combined, which I think is just under 9%. So the entire state itself acts as, I think it was 80% of the wetlands for the entire country. So that being said, only 41% of those wetlands have been actually mapped, of which 30% have been digitized, so digitally mapped. The other challenges facing wetlands in Alaska, the biggest one being climate change. Specifically, since 1970, the air temperature throughout the entire state has increased by at least 1 degree on average. And this has led to a lot of different things, primarily in the North Slope. This has led to permafrost degradation, which has led to draining of wetlands, but also the erosion of wetlands through features called thermokarst features, which is basically when the permafrost explodes through the ground and actually erodes the surrounding habitat. Furthermore, it also has increased the likelihood of wildfires. This is primarily due to lightning strikes. As you can see, just this year alone, there have been 561 wildfires in Alaska. And then, as you can see, the lightning strikes, just in the last 10 days, there have been 2,237. Obviously, not all of those contributed to wildfires, but I believe it was 3 or 4 that have recently started. The final challenge for the North Slope is the oil exploration. For those who don't know, the Alaska pipeline runs through all of Alaska. It's, I think, 740 miles, give or take. But it runs from Prudent Bay, which is the top, one of the highest cities in the North Slope, and runs all the way down to Valdez. So that's a high majority of the oil that the United States produces runs through that pipeline. But along with the pipeline, there is also seismic lines, which it comes from oil exploration, specifically when they used to dynamite stretches of land to see if there's any oil in the land. Along with those seismic lines come abandoned oil exploration sites. Specifically, if you look at the picture, this was an abandoned site that was abandoned in 1972. I was able to actually go visit this site, but it's still left drum barrels. There's still the remains of buildings, the remains of a bunch of metal just from that exploration site. And then finally, along with the oil exploration, that means humans are going across the land. So that's either through trucks, through planes, however they're able to traverse the land, they have left tracks because of that. Oops. There we go. So current mapping techniques for wetlands, there's 2 primary techniques. One is digital photo interpretation, which is what I do on a daily basis, and then in-field delineation and attribution. So the digital photo interpretation relies upon a person or AI, depending on how we go forward, with interpreting aerial imagery in order to delineate wetlands. And when I say delineate, I basically mean drawing a polygon around a certain shape. As you can see on the screen, right there is 7 different delineations of the land, and then they are also attributed. The in-field delineation, of which I've gone twice in 2021 and 2022, provides a sort of a basis by way of a conventions document created by those doing the field work who have gone into specific aerial points and delineated either on the ground or via helicopter. And they've also got an understanding of the attributes required in that delineation. So that conventions document basically tells the photo interpreter, here is an understanding of what we see on the ground so that they can map appropriately in their interpretation on the computer. So for the project area, I am doing a project within the North Slope Borough, which is the northernmost borough inside of Alaska. It's pretty much the high point of the United States. It's about 245,520 square kilometers or 60 million acres. The project area I chose was about 100 square kilometers or about nearly 25,000 acres, primarily because I believed it had a good set of all the attributes and delineation possibilities within the general landscape. There is the 4 biggest things I'm looking for when I'm delineating are the wetland habitat types. So because the North Slope is above the tree line, we don't have to worry about trees. However, because of the temperature how it sways differently depending on the time of year, but also because it's above the Brooks Range, which is the mountainscape that you can see in the bottom section of the north slope. The vegetation can be as small as 3 inches, could be 2 inches tall, and the highest you really get is about 6 inches. And that's usually in the scrub shrub vegetation, but there's also emergent vegetation, and then there's what's considered palustrine open waters. These are usually ponds, and then riverine open waters would be considered rivers. So moving on to the methods section, I will be discussing supervised classification, the data sets, and then the training data. So for a project workflow, in terms of pre-processing, I had to pre-process the Maxar digital globe imagery, a continuous Foliar covered data layer, which I'll go over in a little bit what all these break down into, and then also the division of geological and geophysical survey, hillshade and contour data. After doing this pre-processing, I generated training data for the project area. This training data then was run into a classification on the training, a classification was run on the training data, which generated a classification. Using the classification output, I was able to make an accuracy assessment. And after the accuracy assessment, I basically started the process over and did a second pass through. So breaking down supervised classification, the classification was produced and performed using Esri's ArcGIS Pro, implementing the image classification toolset. Specifically, supervised classification allows for interactivity in choosing the classes, which are then assigned to individual pixels. So I was able to create specific classes based on polygons and their attributions, and then they were applied to individual pixels. Pixel-based classification just again means individual pixels are being are having classes applied to them. But important to note is that neighboring pixels do not have input on the class decision to individual pixels. Finally, as part of the pixel-based classification, I used the support vector machine for my main classification style. This separates data into different classes via higher dimensional field space. And in doing so, it should lead to less noise, less interruption in the correlated bands, and less distraction, I guess you would say, from unbalanced class numbers. This was important because a lot of the delineation and attribution that I ran into, or that I did for this project, some only had like 1 or 2 actual attributes within their class, whereas some had over 20. So having that less susceptibility to unbalanced class numbers is important. So the data sets for the training data, my primary data set was the Maxar digital globe imagery. It is a multispectral 50 by 50 centimeter resolution imagery set. It was collected between 2003 and 2020. I believe a majority of the tiles for my specific project area were taken after 2010. For the actual training data, I was aiming for a 5-acre target mapping unit. This basically means that every polygon that I created had to be at least 5 acres in size or more. This excludes the attribute PUBH, so it's palustrine, unconsolidated bottom, and fully flooded, because they only have to be at least 1 acre in size or more. Important to note with the digital globe imagery, because it was captured over so many years, image stitching needed to happen in order for the data set to look as clean as they could make it. So in some areas, there may be a prevalence of cloud, whereas one image over, it might be clear. So it just depends on what actual imagery you're using. Thankfully, the image I had was pretty clean overall. And again, I use this as the finalized imagery data set for my classification. The second data set that I used for my training data was a continuous foliar cover layer. It was developed in 2021 using vegetation data classes from between 2000 and 2020. It has 16 distinct vegetation classes, of which I only primarily focused on the emergent and the scrub shrub vegetation. With those 6 classes, I was able to generate 2 heat maps for analysis of the vegetation, 2 for emergent, and then 4 classes for the scrub shrub layer. If it's important to note, if any vegetation data was unavailable for a specific area, the topmost layer, whatever that may be, was used in place. And then finally, I used it as a collateral data set for vegetation attribution during my training data delineation, using it as a collateral in place of the knowledge that I've gotten from the conventions documents made in field. Finally, I used a hillshade provided by the Division of Geological and Geographic Survey as slope analysis for my training data. So the initial training data preparations. So the first run through that I did of training data, I ended up with a test area that included 69 polygons, of which you can see the breakdown of how the pixels were broken out. Important to note, this only constituted about 1/4 of the entire imagery or the boundary that I was doing. Furthermore, for the second training data, this was after I ran through a first training session all the way through. I included, it was 70 more total polygons in the second training, again broken down into individual classes and then applied to the classification. So on to the results and the accurate assessment. This is the initial training classification output that was created. Overall, you can see that there's a level of inability to actually understand what certain aspects of the classification are. This is primarily due to it being a pixel-based classification. Each pixel is being affected by the various classes that I've made. That said, I ended up with a 44% accuracy based on the accurate assessment, which required me to individually go and choose. There was, for this project, there was 137 points that were randomly assigned throughout the imagery area. And then once the classification was finished, I went through and assigned a level or a attribution to what I believed each random point was, and that allowed the accuracy assessment to take place. And then a confusion matrix was made off of that accurate assessment. So for this initial training run, I got an accuracy of 44%, which is okay, it's not the best. So after this initial training, I went through and made a second classification. This was the results of that second classification. I think in areas, they are a little more accurate. Again, it's still very hard to understand what all the information is because it's a pixel by pixel basis. But the additional 70 odd polygons allowed for a little bit more breakdown of individual sections. This, again, after an accurate assessment, left me with an accuracy of only 33%, which is, again, decreased from my first initial one. And I think primarily this is due to the size of the polygons that I was creating, which will be reflected later in the discussion portion. And now moving on to the conclusions of the results, or discussion of the results, sources of error, and then future considerations. So the primary limitation of the project is lack of previously mapped data to reference. As there's no previously mapped data for this project area, all the mapping that, or all the delineation and attribution that was done by me with the limited field work that I had to work with. The second limitation was really the detail of the mapping, because I was doing a pixel-based classification. What probably would have worked better is a 1 acre TMU. So instead of having each polygon be at least 5 acres, the polygons are single acre. This would allow for smaller polygons to take place and a little bit more detail to be drawn out in each one of those polygons. And again, that was because I was using pixel-based classification. The output sort of got really messy because each pixel was being affected variously depending on the machine learning. Instead, what might have been better is the other supervised classification style put out by Esri, which is object-based classification, because instead of doing a pixel by pixel classification, it groups pixels into objects. And this would have been more beneficial once I figured that out, because of the size of my polygons. The smallest ones, I think, were like 7 or 8 acres. So it just does not bode well and doesn't contribute well to the classification when each pixel of that 8 acre quad is being assessed based on all the classes available. Sources of error. There is an inherent error in photo interpretation. Each individual has their idea of what a delineation or attribution should be and what it should look like. So all the calls are being based on level experience and knowledge of the landscape. With limited referential data to base decisions on, you only have so much possible delineation and attribution calls that you can make effectively. Furthermore, using the Foliar covered data set for vegetation attribution, the authors specifically advise against making arbitrary attribution calls based on the data set because it's supposed to be used as a continuous vegetation land cover rather than very specific points. You can say, hey, this is exactly what this vegetation should be, and also because of the topmost layer usage. Finally, the accurate assessment based on the pixels. In an initial polygon, they were mapped at 5 acres. And because the classification was completed with pixel-based classification, each polygon was being assessed. So when you did the random points, it was picking out only minute sections of the polygon rather than the polygon in its entirety. In terms of future considerations, the most would be the viability as a collateral data set. What I was trying to do when creating this project was make a viable collateral data set that could be given to interpreters as reference point to say, hey, this is perhaps where a certain polygon should be placed based on this machine learning. Put one there, therefore making the mapping faster. And I think this can be changed in the future based on more detailed mapping. If you're able to get either 1 acre TMU or even closer than that, I'm not quite sure how that's possible, but getting more detailed mapping and allowing a wider variety in the classification in terms of your delineation and attribution calls, I think it could be more viable as a data set. Furthermore, the applicability to future mapping, again, photo interpretation versus machine learning. How much longer are we going to rely solely on photo interpretation for mapping the wetlands versus what machine learning possibilities are there out there that can either aid or take over photo interpretation, at least done by a human. And then also the time and money for future research projects is sort of the biggest thing. Outside of school, a project of this nature would cost thousands of dollars, along with requiring many, many, many hours to actually fully map out an area. As previous people have noted, specifically PAIR, the program or processing power of a computer or a server, whatever it may be, is limited to what you have. So if you're able to get an entire server farm to put behind your classification, you're able to get a lot better, more high detailed classification outputs than you are with, say, a single computer. These are the references that I used for this project thus far. And then that is all I have. So I will now put it out to you guys to see if you have any questions.
All right, thank you very much, Ian. And Ian has a nice email listed out there for people. If you do have any comments or suggestions beyond our evening here tonight, there is his direct email that you may reach him at least time of the presentation here. And so did anyone have any global, well, maybe I'll start this time. And in terms of kind of a question, Ian, I appreciated your sources of error. And I think throughout our presentations tonight, people alluded to that or chimed in on something to that effect. And in knowing your project and a lot of what you do in your work and in this project, Alaska's vastness of where you are, what do you think is really usable? Does Alaska have enough usable, I'll just call it the images for photogrammetry that can make your work a little bit more accurate, or is it just the limitations of those years? I mean, I don't know what percent of Alaska is really, I would call it sufficient imagery, if you will, for your work.
No, great question. I think overall there is a wide breadth or a good variation in imagery. The setbacks thus far is simply time and the lack of people that have actually mapped areas. That's the biggest thing. We have plenty of really nice imagery now. They're starting to come in, I guess I should say. We just haven't been able to actually map any of it thus far. Input like the last status and trends, which is how wetlands are performing in the state. The last status and trends was produced in 1994. We haven't had one since because there's hasn't been enough data produced to actually change anything. So I think it's entirely dependent on what's actually been mapped, and not enough of it has been mapped to understand everything appropriately.
Yeah, it seems just the last frontier is sort of true in that for data as well. And one thing I was going to comment on just for as well is that in some classes we talk about identifying internal sources of validity. And you brought this up, which I'm glad you did, or at least you listed it out here toward the end of your presentation, was that there could be sources of error coming from the user. We call that, either the data entry source of validity, internal threat, if you will, to validity, and how that person is coding that. Now, this is I think a great opportunity to say, how do you combat that? How do you, for you and taking a look at all the data, when you're breaking that down, it's a little bit more than subjectivity, but there's a potential threat to the internal validity of your data. In other words, is your data correct? And could you comment a little bit on what you do that is a way to remedy that?
Yeah. So the primary thing to be done, this project is done as a output for the NWI, which is the National Wetlands Inventory. And part of producing data for that inventory is there's a specific tool set provided usually by the Fish and Wildlife Service that you can actually run these tool sets on the data and it will return various sources of error within the data. So this includes mislabeled polygons. It includes mislabeled or missized ponds or lakes. So for instance, in my target mapping unit, a lake is any open water body source that's above 20 acres. And then a pond is considered a open water below 20 acres. So this tool will go through and establish a boundary around each open water and measure it. And if it is, say, attributed as a lake, but it is under 20 acres, it is then flagged as an error so that a person can go back through and change the attribution appropriately. For instance, the last time I ran the tool, I ended up doing 10,000 polygons as running through the tool. And I think for the first round, I ended up doing, I think 5 rounds total with the tool. The first round, I produced 300 sources of error within the project as an entirety. That's not specific to this project necessarily, but can be applied to it in the future if I was to expand upon it.
Yeah, good. Yeah, thank you.
Yep.
Thank you. And also,
Yep.
you know, the training essentially, you know, having everybody, you mentioned the tool sets, you know, the consistency of interpretation helps to,
Yep.
to suppress those threats. So yeah, thank you very much.
Yep.
Other
No problem.
thoughts, questions for Ian?
Nice job, Ian. Interesting
Thank you.
topic. I was curious if you had a chance to dive into the classifications to figure out if there were some that were contributing more or less to the overall error, like if there were some types of wetlands that had really strong accuracy and
Yes.
others where it had more trouble, and what might be causing that difference.
Yeah, so that's where the confusion matrix comes in. As you can see along the bottom on row 18, that is the accuracy produced by the machine learning. And then if you scroll along, sorry, I have to move a thing. If you go to what is U accuracy, that is the user accuracy. So that is me personally going back through each point that was produced by the accurate assessment and marking whether or not it was accurate to what I believed it was accurate to. So there are some, say, specific PEM1F. The accuracy assessment didn't actually place a point on a PEM1F that I saw. So it gets a 0 in terms of the accuracy from the machine learning, because it applied, I think there was maybe 4 or 5 points that it called PEM1F, but wasn't actually PEM1F. So there's that. You can go along all the different attributes and see whether or not they're producing well. Overall, like PEM1, SS1C, there was only 2 actual polygons attributed that way. So it got 100% accuracy because when I went back through the points, they were correct. So it's sort of, again, dependent on what I myself put in the accuracy assessment as the final call relative to what the machine says.
Thank you. Yeah, that's a
Yeah.
lot goes into calculating accuracy considering underlying data and then how many sample points. And so I just curious, as you were looking through, did you observe any trends or things that you thought, oh, I think it's having trouble picking up this in the imagery, or it looks like it's confusing open water with some other landform? Or
Yes. So mainly because of the pixel-based classification. So if you look at these pink open water body sections, the pixels based on the second training are really diluted because it's interpreting on a pixel basis that certain pixels are, that color is probably maybe PEM1 SS1E instead of PUBH. So I think it's if there were, if it was done as an object class instead of a pixel-based classification, I think it would be able to capture those whole features rather than being broken down into individual pixels and then disrupting the classification. If you actually look back, the first classification I ran, the top right pink is actually a lot cleaner looking than the second assessment, but I had less inputs basically. So,
Thank you.
yeah, no problem. Thank you.
All right, other questions or comments for Ian? Per?
Ian, great presentation.
Thank you.
Thanks for sharing with us. I'm curious, you've been up there, 2 years in a row now, and you talk about maybe some of the threats to the habitats up there. What would you recommend for sort of a refresh, going forward on how do these landscapes change, and how would you keep a data set accurate, kind of based on what you've seen year over year?
Great question. I think trying to keep it accurate is probably the hardest thing to do. So I know as GSS, we did basically the very first mapping of the northernmost part of the north slope. And that was done in 2005, I want to say, 2005, 2006, somewhere in there. And as of right now, that is the only mapping of the north slope that is fully complete and given to the NWI. So being able to readily assess how climate change and the natural changing of habitats up there has changed just in the 20 years since we produced that data. I know already we're trying to go back and change how we attributed areas, mainly because we've now introduced different attributes to call them. So it's sort of developing, but I don't think, at least right now, with the production levels happening in Alaska, I just don't think it's necessarily possible to stay super, super, super current, unfortunately.
Kind of a moving target.
Yeah, exactly. Imagine it's, I guess, you're standing on the ground and it's a bullet train and you're just trying to splatter attributes on the bullet train. That's what we're trying to do. And we're slowly getting there, I would say. But like, I can use a great example. In the project area I just went to, we had 5 or 6 points laid down that we were able to visit on the first day of our flying. And we actually visited that same spot 3 hours later, and the entire place was on fire because it was a wildfire covered over all the points that we had just made. So that wildfire completely changes and or destroys all the habitats that we just analyzed. So how are we supposed to, what are we supposed to do with that? So yeah, it's difficult.
Great points. Great discussion. Any other comments or questions for Ian? All right, Ian. Well, on behalf of all of us in attendance here tonight, and hopefully some of the folks who had to leave earlier can come and watch the second, yours and Annika's presentation later. But on behalf of all of us, congratulations to you, Ian, as we get closer and closer to the finish line. This is nice to see. And once again, Ian has his email up there. If anyone wishes to contact him about anything or provide him feedback, please feel free to do that. But otherwise, Ian, congratulations to you too. Again, the finish line is getting closer. We're not there yet for all of us here tonight, but we're getting closer as part of the preliminary work here. So very good. And thank you again, Ian. And with that being said, we will stop the recording here and visit about what is next. So again, congratulations to all of you.